In Chapter 9, we're going to have a brief introduction to what is actually quite a very large topic, differential equations. This is a quote from our current Math 254 textbook, which is the Differential Equations course. This vast subject lies at the heart of mathematical modeling and is used in engineering, physics, chemistry, biology. I've added in statistics and probability because that's true, geophysics, economics, finance, and health sciences. So it's kind of a big deal, and we're not going to get into the weeds too much with it. We just want to learn some basics that might be useful in different engineering and physics courses until we can take Math 254. All right, so let's start with some basic ideas of differential equations. Okay, so an equation that involves derivatives is called a differential equation because differentiating is the process of taking a derivative, remember, because of the difference quotient that we learned about in Calc 1 first thing. So some examples would be y prime equals 3x, y double prime of x equals negative 32. That one should look familiar to you. The second derivative with respect to x is this lovely function here, plus 14 times the first derivative. Interesting. So that involves both the second derivative and the first derivative. This also involves the second derivative and the first derivative. So the family of functions that satisfy a differential equation is called a general solution. Now let's look at that just a little bit and talk about what that means. So I have f prime of x is equal to 6x plus 2, which is this line right here. So if you look, this line is f of x, and which I labeled right there, f of x, which is 6x plus 2, or f prime of x, sorry, f prime of x. So that's a derivative. And then the question is, what function satisfies it? Let me show you in Desmos really quickly. So f prime of x, I fixed the label, f prime of x is equal to this lovely line here. And so then the question is, what functions would have this as its derivative? Right? That's what you're looking for. So of course, since it's a linear function that's the derivative, then it must have been a quadratic that is the solution. Let's prove that. So if I have a derivative, f prime of x, so that would be dy dx equals 6x plus 2, then that means that I need a function that would have this as its derivative. So dy would be equal to 6x plus 2 dx, right? I'm multiplying both sides by dx. And then all you do is integrate both sides. So you say, okay, I'm going to take the integral, I'm going to take the integral. And so the integral with respect to y would be y, and the integral with respect to x would be, well, the integral of 6x is 3x squared plus 2x plus a constant. And that's why I'm drawing so many of these curves, because there isn't just one solution. There's infinitely many. So if I set my C into motion here, you can see that there's lots and lots and lots of solutions, infinitely many, in fact. There's infinitely many parabolas that would have that black line as their derivative. That's what it means when it says there's a general solution. And so that's what we'll write on our notes, right? There are infinitely many solutions. And that's what the curves are showing us on the graph. And it's because of C, right? That constant C, right? Because of that, we can have infinitely many solutions. That's what a general solution is. So a general solution would be plus C, so it's technically in motion. There's technically infinitely many of them, or it's all of them at once, if you will. All right, so this is an important comparison to think about. When you solve arithmetic equations, which was, I realize, a very long time ago in your life, your solutions are numbers, right? So for example, everybody knows, oh, 6 plus 2, that's 8. Woohoo, right? When you solve algebraic equations, what you get are variables. You'll find, subtract 2, That's 12. 6 divides into 12, so you'll get x equals 2. But it's important to note the x equals. You'll get variables equal to a particular value, right? But it involves the variable x. When you find the solutions to a differential equation, that's right here. That's the solution. It's the general solution. And so you're not coming up with a number or a variable, you're coming up with a function. So for example, when we did f prime of x equals 6x plus 2, then f of x was equal to 3x squared plus 2x plus c, plus a constant. All right, so there's two ways we can do this function thing. So we can have a general solution, which has infinitely many answers, right? Think of the Desmos graph in motion, right? It's because of the plus c, plus of that constant. You'll have infinitely many answers. So just remember this graph, right? And there's more besides that. I've limited my motion to between -5 and 5, but of course it technically goes from -infinity to infinity. But we don't have that kind of time to wait for Desmos to graph that. All right, so what if I turn off the general solution and I want a particular solution? A particular solution happens when you are given an initial condition. An initial condition is a specific piece of information that often accompanies a differential equation and allows that arbitrary constant, right, which we know as plus c, on the back end of your integration to be determined. So rather than just saying plus c plus this constant, we can couple that differential equation with an initial condition, and when they are coupled together, it's called an initial value problem, also known as an IVP quite frequently. Right? And then we'll be able to find a particular solution. So for example, if we look at f prime of x equals 6x plus 2, that's again dy dx is equal to 6x plus 2. So dy is equal to 6x plus 2 dx, right? You multiply both sides by dx. And then that cancels over here. So then you integrate both sides. The integral with respect to y of 1, because there's a 1 right here, is y. The integral of this is 3x squared plus 2x plus c, same as before. And then this is equal to f of x. So this is the general solution, just like we saw before on the previous page. I just reran it. Okay, but now they gave us an initial condition. The initial condition is that f of 1 is equal to 2. It's right over here. That's an initial condition. Something set in stone about this function. All right, so then I can take that f of 1 equals 2 and I can substitute it in. Sorry, I just realized I wanted to change my color choices. All right, so f of 1 equals 2. So 3 times something squared plus 2 times something plus c is equal to 2. And that is 1 in here, right? Because those are x values. This is x, this is y. So 3 times 1 squared plus 2 would be 3 plus 2, which is 5. So 5 plus c is equal to 2. So c is equal to -3. And that means that our particular solution, not our general solution. The general solution is the one that's in motion. But the particular solution would be f of x equals 3x squared plus 2x minus 3. The particular graph that's drawn right here. So it has a specific value because it has to go through the point right here. See the initial condition? 1, 2, right there. So there's your initial condition, is that it has to go through that point, which means that it must be this curve, not any old curve. And you can see that on the Desmos graph. So the particular solution has to go through that point, 1, 2. Therefore, it's this lovely curve right here, as opposed to all of the curves, right, which is no good to us. That's the general solution. So the general solution is that red one. It's floating through. And the particular solution is the one that goes through the specific point that was given in the problem.